So on this lecture, we're going to go through the normal Zeeman effect. So before I go into this Zeeman effect, I just wanted to remind you, remember we said H on psi equals E on psi, where H was the kinetic plus the potential. It was PE squared average over 2m of the electron plus U of R. There was our energy operator. But remember, the proton does move. Remember when we did the Bohr atom, it's the center of mass of the proton electron that's not moving. So H really should be PE squared all over 2 mass of the electron plus the proton does a little bit of moving too, P of the proton squared all over 2 times the mass of the proton plus U. There's only one potential. So that's really what the H should be. But remember, when we did the Bohr atom, we said we could write this all in terms of 1 if we just replace our mass with mu. So really, our H should be PE squared all over 2 mu plus U of R. And so where mu, we said was the reduced mass, and which we said was, in this case, it's the mass of the electron, mass of the proton, all over the mass of the electron plus the mass of the proton, which affects it a little bit. And so all we said is we just, instead of handling the H this way, we can just go back and replace every place where we had the mass of the electron, we replace it with this. Okay, and we already knew that for the Bohr atom, but I just didn't put it in for the hydrogen atom. So that takes into account the movement of the proton right there. Okay, I just wanted to go over that. Okay, so now I wanted to look at what we call this Zeeman effect. The Zeeman effect is usually what happens when you put a magnetic field on an atom. But let's look at our hydrogen atom. I'm going to look at it again, our classical picture of it. What do we have? We have a proton here, and we've got some electron orbiting around it. Remember, this is just a classical picture right here. Here's our electron. It's kind of going along this way around it. And we know that there's an orbital angular momentum. Remember, we already defined it right here. Orbital angular momentum is this. But we do have an orbital angular momentum, L, and that, again, in classical physics, it's defined as R cross P, where R and P are perpendicular because R goes from the proton out to the electron and P is going around, so they're perpendicular. So this is just R times P, and the direction of it is going up this way. So this angular momentum is going off in that direction. I don't know what I should call that. Out. I'll call that out, say. Which is RMV, since momentum is MV, out. Okay, this is also since we have a charge going around in a circle, if you remember from electromagnetism, there's a magnetic dipole moment, mu. If you remember from classic electromagnetism, this is defined as I times the area, where the area would be perpendicular to this plane, and then you just run around which way the positive charges would go. Well, if the electron's going this way, that's like a plus charge going around this way. And so if you just run your right hand around, mu is actually going in the opposite direction. Right there, there's mu. Mu is in the opposite direction of L. Okay, and if this has some radius, say r, well, the I would be, there's an electron going around. I'm not going to worry about the direction because I already know they're going to be opposites of each other. It goes around the this is charge per unit of time, so every period it goes around once, times the area, which is pi r squared. Okay, and we also know that the velocity of it going around is the distance over the time. That's 2 pi r all over the period, or 1 over the period from right here. 1 over the period is equal to velocity over 2 pi r. Velocity all over 2 pi r. So I can put that 1 over the period right there into here. So this is e pi r squared times this, times v all over 2 pi r, which is, I cancel an r and a pi, so if I cancel an r and a pi, this would just be e r v r all over 2. And it would really be in the opposite. If we called this out, I guess that would be in. Okay, and well, you noticed from this one right here, I can solve for VR out of this. It's L over M. So VR is equal to L over M, the angular momentum over the mass. And so I can put that into here. Since this is defined as out and this is defined as in, there's going to be a minus in there in between them. So we get mu which is equal to e over 2 VR, which is L over M. L over M. And we said these two are in opposite directions. Since one was defined as out and one's defined as in, I guess I need to put a minus there to handle the opposite directions. So there is what the mu is right here. Now what I'm going to do is I'm going to multiply, put an h bar up here and divide by an h bar. So it's mu is equal to e h bar over 2m L, there's a minus there, L all over h bar. So there's the two h bars I put in. Now this quantity right there are constants. That's the charge of the electron, h bar, twice the mass of the electron. We're going to give that a constant, call it mu b. It's called the Bohr magnetron. Bohr magnetron. Okay, and it's just from fundamental constants. And this thing is 9 times 10 to the minus 24 joules per Tesla. Or if you want to put it in EVs, it's 5.8 times 10 to the minus 5 EV per Tesla. Okay, so it's an energy per magnetic field. Okay, so I can replace all this with mu b right here. So this A lot of mu's here. But mu b is a constant right here. It's these numbers. But mu, the magnetic dipole moment of the orbital. Matter of fact, since this is going around, well, we should, since this is orbital angular momentum, I should even put a little L there, meaning it's due to orbiting, the orbiting electron. So that little is due to orbiting. Okay, so this becomes mu is just equal to minus mu b, looks like it, minus mu b L over H, all over H bar. Okay. So there's the relationship, but we always want to put everything in terms of angular momentum because angular momentum is one of the few things we can measure. Right here. We already know how to measure angular momentum. I'm going to do one other thing to this. I'm going to, there's my mu. I'm going to put another letter in here. I'm going to call it G sub L. Mu B L all over H bar. Where G sub L, I'm going to call the orbital G factor. Now you say, how can you just throw in a factor? I can because it's 1. G is equal to G sub L is just 1, so I can put it in there. It has no units, it's just a number right here. What is it? It's kind of we'll see a little bit later, but it's kind of a measure of how the charge is distributed versus how the mass is distributed when you're going in a circle. Here it's just a point charge all out at the edge going around. If this were a different shape, it might be a different factor in front, which we'll see. Okay, so now we have a magnetic dipole moment right here. So this is like a magnet, like right here. So, well, what happens if we take a magnet and put it in a magnetic field right here, a mu? Well, so first of all, let me box this in right here. So let's say we put this in a magnetic field. Let's say the magnetic field is going in this direction, in the z direction. So B is in the z direction, a constant magnetic field. Well, anytime we put a magnetic dipole in a magnetic field, we know that, first of all, we know there's a torque on it. We know there's a torque given by mu cross B. So there's a torque on the system right here. Okay, and so there's going to be a torque on this system right here, and what it's going to do right here is it's going to want to precess around this way right here. So I'm going to redraw it over here. So here's my L right here, and here's the z direction, and it's going to precess around this axis right here. Let me just call this angle right here theta. So here was my electron going around, and there was my L, or mu. Mu is also going to precess exactly like L does. They're back to back right here. Well, we know also, besides the torque, is defined as the change in angular momentum with respect to time. So that was just a classical result right there. Okay, so if we look at this thing, since this thing's precessing, at this instant it might point to there. A little bit later, it's over here. It's moved through some angle, let's call this angle phi, going around right here. So this angle is going around. And we could even say for a little d phi, it's just equal to r d theta. Or actually, we can just say omega is defined as d phi dt, where this is the angular frequency of it going around. So d phi is equal to omega dt. Also, we can say that the little dl, which L was pointing here, if we look at it from up above, it's a circle right here. If we look at it from straight up above, and here is this line, and another line just a little bit off from that. This is my d phi, and the change in L would have been from here to here, because L used to be there, and then it moved over here, so the change in L is this length right here. There's the delta L. And this length from here to here, from this triangle, if that's L, this length must be L sine theta. This is L sine theta right there. So if this is L sine theta, and we know we can get delta L. Delta L is equal to S, just like S equals R theta. There's my S, which is delta L, equals R, which is L sine theta. L sine theta d phi. But my d phi is omega dt. Okay, so there's your delta L right here. From here, we can also get delta L from this equation right here. You notice, since B is in the z direction, if we cross this product, I don't worry about the direction for a minute, the cross product is the magnitude of this times the magnitude of that times the sine of the angle between them. Well, B is here, L is there, or mu is here, theta is, it's going to be the, mu is here, B is up here, and so what you get is, you get the angle between them is 180 minus theta, but the sine of 180 minus theta and the sine of theta are the same thing. So really, this equation right here, if I bring the dt on this side, I get, well, we'll keep it there, dt, and we get the magnitude of mu, magnitude of b, sine of the angle between them, which is the sine theta, and that equals dl, or sorry, this should have been dl too, right here. dl. So I got dl two different ways, one from the geometry and one from this definition. Since they're equal to each other, I can just equate these two right here. If I just equate these two, the dt's are gone, the sine thetas are gone, and we can solve for the angular frequency that this thing precesses around. So this omega is equal to mu b divided by L, mu b over L. Sorry, mu big B all over L. And this is my little L there, it's my orbital right here. This is a special frequency right here. This is called the Larmor precession frequency. It's precessing around. Precession frequency. Frequency. Precession. Still not right. Precession. Frequency. Okay, so what that means is you put hydrogen in a magnetic field, and it's just going to precess at that frequency right there. Okay, and if it can't lose its energy, it's just going to keep precessing right there. It's just going to keep precessing around. Now, what about the energy? There's another formula they give you when they talk about magnetic dipole moments besides this one, and that is the energy, the potential energy of a dipole. U of a dipole It's just defined as minus mu dot B. Go back and look at your electromagnetic books right here. Okay, and so, and since our B is in the Z direction, when you dot this right here, remember you can, instead of using the cosine of the angle between them, we could just say it's the components. Mu in the x times b in the x plus mu in the y times b in the y plus mu in the z times b in the z. Well, the only b I have is in the z, so u is just going to be minus mu z times b, because the only b I have is in the z direction. Okay. And we already said what mu was right here. We said mu was this. If mu is that, then what's the z component of it? Well, this is all a constant, so all it's going to do, if I have the z there, it's just going to bring the z over to this. So mu z, the z component of the magnetic dipole moment, is just minus GL mu b times the z component of the L all over h bar. Okay, and now I can put that up into here, and we can get the energy, dipole energy, right here, UD is equal to, well, it looks like it's going to be positive because I have a minus, I have another minus here. So it's just going to be this times B. So it's going to be G sub L mu B B L Z all over H bar. So there is the energy associated with that. But for our case right here, we want to find out the energy, and so this is an operator, so I guess I could just turn this into an operator. UD operator, I guess, is just equal to this with an operator over here. G sub L mu B B L sub Z all over H bar. Okay, so there is my energy operator. So now what I can do is, if I go back to this equation, my original equation, H, so that's going to be the potential plus the kinetic, right? But not that potential. Maybe I'll put a little O. That's our old Hamiltonian. Acting on psi gave us what? It gave us our energies acting on psi. Okay. But now we have a slightly different H right here. We have what we had before, but now we also have that one. So now it's H plus U acting on some wave function equals some new energy. Maybe I'll write it as E, what we had before, plus some delta E, plus some change. It changed somehow, times the new wave function right here. But you'll notice here, this eigenfunction solved was for this operator. We've now changed the operator right here. So if I change the operator, it's probably not going to, this wave function is not going to work. I'm going to need a different wave function. Now, this one was hard enough to get. Remember, this thing took the last 10 lectures at least to get all of this in. This thing, I'm even making it more complicated. I certainly don't want to do that. But there's something that will simplify this. There's something called perturbation theory. that says if this is a small effect, so if your whatever you're adding to this is small for a small effect, then if I wanted to get how much the energy is just going to shift, delta E, because that's really what I wanted right here, all I have to do is go back to my original wave function, which I know, and just sandwich in my UD. You just find the expectation value of that. That's for the first approximation. This is very good as to what the change in energy is right here. So I don't really have to go back and solve some big complicated. All I have to do is just solve this right here. And this I know because I know size and I know my use of D. Remember, when we do it like this, it's really an integral right here. So really what we meant is this is an integral of psi star UD psi, and we're integrating over r's and thetas and phi's. So instead of putting three integrals, I'm just going to say dv for d volume. You're integrating all over all three of them. Okay. Well, this is delta E. Delta E. Okay, this isn't that hard to solve now because I'm going to put in what UD is. It's right there. I'm going to factor out whatever, pull out in front of the integral, everything but the LZ, because these are all constants. So I have a G sub L, mu B, B over H bar. Then I have the integral of psi star. Now the only thing left with the UD is L sub Z, operator acting on psi and integrating it over the entire volume. Well, whenever you operate LZ on psi, it just becomes, we know LZ on psi is just M sub L H bar on psi. So I'll just replace this with M sub L H bar psi. Okay, and I can bring out the constants, the ML and the H bar, so that delta E is equal to G sub L mu BB over H bar. And then when I LZ on psi, it gave me an M sub L H bar. I'll bring that out in front. M sub L H bar. And the only thing left in the integral is psi star psi. D volume. And what is this? Well, isn't that our normalization? That's just one. So I don't ever have to integrate anything right there. So it looks like the energy is going to be shifted, and we can cancel an H bar here. The energy is going to be shifted by G sub L mu B B M sub L. So there is how much our energy gets shifted. Remember, G sub L is just one, so this is just one. I could take that out if I wanted to. Okay, well, what does this do to our spectra? Well, here's our spectra. N equals 1, right? And then we've got N equals 2. And then I'll just show it for 3 of them. N equals 3. Well, when N equals 1, we already know what L can only be 0 to 1 less than this, so it can only be 0. Okay, and so when I put in, so this right here is the energy I get when there's no magnetic field, no magnetic field. Okay, and then what happens to it when I put it in a magnetic field? Okay, well, first of all, this is how much the energy shifts by. But for an L is equal to 0, m sub L equals 0. And so the energy doesn't shift at all because this would just stay the same. So this would stay exactly in the same spot. Well, what about this one up here when n equals 2? Well, L can be 0 or L can be 1. Well, when L is 0, there's no shift. So it would be right there. But because m sub L can only be 0 here. M sub L is 0. Over on this case, m sub L can be 1, 0, or minus 1. So that means when it's 1, this is 1, that's 1, it shifts up by mu BB. So it's going to come up, it's going to shift up right here, and this distant difference right here would be mu BB. And then it's also when m sub L is minus 1, it's going to shift down by mu BB. These gaps would be exactly the same right here. So it'd be mu BB. Now, this one up here, we got L can either be 0, or L can equal 1, or L can equal 2. And over here, m sub L is only 0. Here, m sub L can be 1, 0, or minus 1. Over here, m sub L can be 2, 1, 0, minus 1, minus 2. Well, this is just going to, this one doesn't shift at all. This one shifts up and down by mu BB. This one shifts 2 mu BB, or 1 mu BB, or 0, or my. So really, this is going to shift into 5 of them, all of them, right here. So this is the case where m sub L equals minus 2, minus 1, 0, 1, 2. And this is the case m sub L equals 1, 0, minus 1, and this one's only 0. So what we used to get, if we were to draw on here, let me just say this is our spectra going across here. Remember, we did the hydrogen spectra. We saw that the jump from the 3 to the 2, that was a red line or something when we looked at it. It was some red line. Well, there's also a jump from 2 to 1. We couldn't see that. That's in the ultraviolet part of the spectrum. But let me just put it over here. So there's so this is, let's say this is the 3 to 2. And then let me put the other ones in a different color here. How about from 2 to 1, let's just put it over here. There's 2 to 1. And then there would be one over here, 3 to 1. That would even be bigger. Maybe I'll put it over here further, right here. 3 to 1. Okay, those would have been the 3. If we could have seen these, we would have only seen that because you only see lines that jump to the second level. But you notice that would have been the lump jump from here to here, or the jump from here to here, or the jump from here to here. Those are the 3 lines. Now, what would those 3 lines do in this situation? Well, the jump from here to here is exactly, what do we say? That's 2 to 1. If we look at the 2 to 1 right here, so we'll look at this one right here. From 2 to 1, from here to here, that's exactly the same spot. So it wouldn't do anything to that because the energies. Now this one from here to here would be slightly lower. It would have dropped a little from here down. This would have been less energy. Since my less energy is going that way, it would have given me another line right there, shifted over by mu BB. And this one right here would have been slightly bigger, and I would have had a line over here where these spacings, the spacings would be mu BB. Now, what about from 3 to 1? 3 to 1. Well, from 3 to 1, remember, first of all, remember we have a selection rule for the mass, M sub L, right here. M sub L, delta M sub L can only be 0 or plus or minus 1. So, you notice I cannot jump from here down to here because that went from minus 2 to 0. It changed by 2, so it can't happen. But let's start with this one right here. From here to there, that can happen. But that would be exactly right here on this line, 3 to 1, because that's where 3 was and that's where 1 was, right there. So that would be right there. Now I could go from here down to here, because you went from minus 1 to 0, and you can make a minus 1 to 0, and that would have dropped it by a mu BB. So it would have put it over on this one side right here, or mu BB would have put it right there. And I couldn't have gone from here to here because you dropped by 2, but I could have gone from here to here because you went from 1 to 0. So I could have also done this right there. And that would have put it on the other side right here. That would have put it over here. Okay, and those are the only ones that would have jumped because I can't go from 2 to 0. Okay, and then what about from 3 to 2? From 3 to 2. Well, from 3 to 2, that was this line right here. And so if I went from 0 to 0, or from 1 to 1, or from minus 1 to minus 1, they would have all been right on here because these all shifted by the same amount. So they all dropped the same amount. So all 3 of those would have just been right here. Now, when we drop from 2, 2 could have only gone to 1 right here. And you noticed here, this one went up 2 mu BB, this one went up 1, and when you subtract them, it's just 1 more mu BB. So it would have just been one line over here. And likewise, when this thing dropped, this minus 2 could have only dropped to here. That's the only way it could have dropped. So you could have only dropped to there. And this thing was 2 down, this was only 1 down, so the difference is just 1 down right here. So it would have been over here on this side. So this is what it would have given me. It would have split all of the lines into 3 lines right here, where the shifting, the spacing between them would have been mu BB. Now, this isn't the whole story, but we'll get to the whole story. But just to let you know, that means when we had that hydrogen tube and we looked at it with the spectrum, does that mean if I put a magnet in front, we'd see these lines split? Well, they would, but they'd be very difficult to see because if you think about this mu BB, how large is the splitting was this, mu BB? And we said what mu B was, it was 5.8 times 10 to the minus 5 eV. 5.8 times 10 to the minus 5 eV per Tesla times the magnetic field. Now, a really strong magnet is about 1 Tesla. That's really strong. So times 1 Tesla. So if we put it in a really strong magnetic field, the Teslas would drop, and this thing would have shifted on the order of, say, 10 to the minus 5 eV. Remember, these distances here are on the order of, 5 eV. Remember, this thing is down in a whole 13.6 eV. But if this were 5 eV, and this is, 10 to the minus 5 eV. That's how much these things split by. That would be 1/10,000th of this distance. You're never going to see that. I mean, that's really small. You'd have to have a really good sensor right there. Okay, but this isn't the full end of the story. But in the 1922, two people, Stern and Gerlach, 1922. Decided to just check this thing out by what they did is, so this is Stern-Gerlach. This is about 1922. They really wanted to see if this really did quantize angular momentum. So what they did is they built this magnet that was non-uniform magnetic field. So if you looked at it at the end, kind of look off like this. And the magnetic field, actually, I'll draw it two views. If I look at it from the end, it looks like this. This is one pole of the magnet, and that's the other pole of the magnet. So the magnet kind of, it's non-homogeneous. It gets concentrated as you go up this way. Okay, so this was the bottom magnet. This is the top one. There's the magnetic field. We're going to let this be the z direction right here. And this is a long, if I can draw this thing, it's kind of a long distance down, this magnet right here. That's the top one. And then the bottom one, it's kind of goes off like that right here. And so what they did is they shot a beam of silver atoms right down the center of that, right down through that magnet. So they're sending down a beam of silver atoms. Now, I don't know why they picked silver. I don't know if they were just lucky or what. Maybe it's because what they did is down here at the end, they had a glass plate. And when the silver atoms hit the glass, you can see silver on the glass right here. So maybe that's why. But okay, and so what that does here is, since this B is non-uniform right here, there is a, since this is the z direction, there is a change in B with respect to z. It varies as you go up this way. There is a change, but they made that change constant. But B is not constant, but the change in B, the derivative of B with respect to z is constant. Constant. Okay, now we already know that the U, we already said what the U was. It was right, the U, or the change in energy. Where did we say that? Right here, the U, right here. Here's our change in energy, our U, is G sub L mu B B M sub L. Okay. And now, first of all, classically, what would you expect if you were to throw a beam down and these atoms acted classically? Well, these remember, we have these different mu's. All the mu's would be pointing in different directions right here. Why? There's no special direction. They'd all be pointing in different directions. And the force, remember, the force in the z, at least the magnitude of the force, is defined as the derivative of u with respect to z. And so if I take the derivative of this, we get G sub L, mu B, that's all constant, M sub L, and then the only thing you're taking the derivative is B with respect to Z. Well, this is a constant. This is a constant, that's a constant. So it looks like the force in the Z is somehow proportional to M sub L. which is related to the Z component. Now, if it was classical, what you'd expect is, since if all the atoms are pointing and mu's are pointing in different directions, the forces would all be different on the vertical force, and you would get kind of a whole mesh right there. Now, if we're talking about our atoms we have here, we know that for this case, m sub L is 0. If you plug that into here, it would not move at all. The beam would you would just get that line. Wherever your beam was here, it would just go straight on through. It wouldn't have any force. You'll notice for this case right here, you would see 3 lines, because you'd see a force pushing it up, you'd see a force pushing it down, and you'd see no force. So you could see that, or you could see 3 lines. Or this case right here, there's 5 different discrete values of m sub L. And so over here, you'd get 5 lines. Matter of fact, the number of lines you should get is 2L plus 1. When L is 0, you should get just 1 line. When L is 2, you should get 3 lines. When L is 3, you should get 5 lines, and so on. It's just, that's what you should get to show the space quantization of angular momentum. But when they did this experiment, they got something totally unexpected. They didn't get this, or they didn't get any of these right here. They actually got 2 lines right here, which threw everyone for a loop right here. Why would you only get 2 lines? Here, you should get 1, 3, you should get 2L plus 1, but you only got 2 lines right here. And so this was a big discovery right here, and on the next lecture, we'll go through what the heck that means right there. Okay.